Hey there, tech explorers. Ever wondered what makes your smartphone so smart? The answer lies in tiny but mighty microchips, and at the heart of these chips is a special element called silicon. Silicon is a semiconductor, which means it can conduct electricity under certain conditions. This unique property makes it perfect for creating the intricate circuits that power our digital world. But where does silicon come from? You might be surprised to learn that it starts as humble sand, or more specifically, a mineral called quartzite. Quartzite is one of the most abundant materials on Earth, found in beaches and mountains all over the planet. Through a series of amazing transformations, we extract silicon from quartzite and turn it into the brains of our electronic devices. It's a journey of epic proportions, from a grain of sand to a super-fast chip. So buckle up, because we're about to dive into the fascinating world of semiconductor manufacturing and explore how these tiny silicon wonders are made. Get ready to be amazed by the power of science and engineering. Our journey begins with quartzite, the sandy source of our silicon superstar. The first step is to extract pure silicon from quartzite in a giant furnace. Imagine a super hot oven reaching over 3,000 degrees Fahrenheit. Inside this inferno, quartzite is mixed with carbon, and through a chemical reaction, pure silicon emerges. But the journey doesn't end there. This newly formed silicon is still not pure enough for chip making. It needs to undergo further purification to remove any impurities that might interfere with the chip's performance. Think of it like refining gold. You want to remove all the unwanted stuff to get to the precious metal. Once the silicon is super pure, it's melted again and carefully cooled down in a process called crystal growth. This creates a single, giant crystal of silicon known as an ingot. Imagine a giant silicon sausage, perfectly ordered and free of any imperfections. These ingots are the building blocks of our microchips. Now that we have our massive silicon ingot, it's time to slice and dice it into thin, round wafers. These wafers are incredibly thin, typically less than a millimeter thick, and extremely fragile. Imagine cutting a loaf of bread into super thin slices. That's how delicate this process is. Each wafer will eventually become home to hundreds or even thousands of individual microchips. Before the chip-making magic begins, the wafers are polished to a mirror-like finish. This ensures a perfectly smooth surface for building the intricate layers of a microchip. These shiny wafers are now ready for their grand transformation into the brains of our beloved electronic devices. But how do we go from a blank silicon disk to a chip packed with billions of transistors? Stay tuned to find out. Now things start to get really interesting. Remember how we talked about silicon being able to conduct electricity under certain conditions? Well, to create the complex circuits on a chip, we need to carefully control where and how electricity can flow on the silicon wafer. That's where photolithography comes in. Imagine you're painting a detailed picture, but instead of brushes and paint, we're using light and chemicals. Photolithography is like using a super precise stencil and a special kind of light to create patterns on the silicon wafer. These patterns will determine where different components of the chip will be built. First, the wafer is coated with a light-sensitive material called photoresist. Then, a glass plate called a photomask containing the desired circuit pattern is placed over the wafer. Ultraviolet light is projected through the mask, exposing certain areas of the photoresist while others remain unexposed. Think of it like developing a photograph. The exposed areas will harden, while the unexposed areas can be washed away, leaving behind the desired pattern on the wafer. This process is repeated multiple times with different masks to create the complex layers of a microchip. Section 5, laying the foundation deposition in chip making. With the circuit patterns etched onto our silicon wafer, it's time to start building the actual components of the chip. This is where deposition comes in. Deposition is like layering the ingredients of a cake. We carefully add thin layers of different materials onto the wafer to create the transistors, wires, and insulators that make up a microchip. There are different methods of deposition, but one common technique is called chemical vapor deposition, or CVD. Imagine a chamber filled with a special gas containing the material we want to deposit. The wafer is placed inside the chamber, and the gas molecules land on the wafer's surface, forming a thin, uniform layer of the desired material. It's like coating the wafer with an ultra-thin film of the building blocks needed to create our electronic masterpiece. This process is repeated multiple times with different materials, carefully building up the layers of the chip, just as you would add layers of frosting and filling to a cake. Section 6. Etching, sculpting the silicon masterpiece. Now that we've deposited layers of materials on our silicon wafer, it's time to sculpt them into the intricate three-dimensional structures that make up a microchip. This is where etching comes in, a process that selectively removes materials from the wafer, much like a sculptor chisels away at a block of stone to create a masterpiece. Remember the patterns we created using photolithography? Well, those patterns now act as a protective mask, shielding certain areas of the deposited materials while exposing others to the etching process. There are different types of etching, but one common method uses plasma, a superheated, electrically charged gas. The plasma acts like tiny energized hammers, bombarding the exposed areas of the wafer and removing the unwanted material. This precise removal process creates the intricate trenches, channels, and features that define the different components of a microchip. Section 7. Doping, enhancing conductivity with ion implantation. Our silicon wafer is starting to look more and more like a microchip, but we're not quite there yet. Remember how we talked about silicon being a semiconductor, meaning it can conduct electricity under certain conditions? Well, to fine-tune the electrical properties of our chip and create the transistors that act as tiny electronic switches, we need to introduce impurities into the silicon lattice. This process is called doping. Imagine adding a pinch of salt to your cookie dough. It doesn't change the overall structure of the dough, but it does enhance the flavor. Similarly, doping introduces a small number of impurity atoms into the silicon crystal, altering its electrical conductivity. One common method for doping is ion implantation. In this process, ions atoms with an electrical charge of the desired impurity are accelerated to high speeds and bombarded onto the silicon wafer. These ions penetrate the silicon lattice, embedding themselves within the crystal structure and modifying its electrical properties. By carefully controlling the type and concentration of impurities implanted, we can create regions of the silicon that are more conductive, or N-type, or less conductive, or P-type, forming the basis of our transistors. Section 8. Inspection and cleaning, ensuring perfection. Throughout the entire chip-making process, from slicing the silicon ingot to doping the transistors, meticulous inspection and cleaning are crucial. Even a tiny speck of dust or a slight imperfection can ruin an entire chip, so maintaining a spotlessly clean environment and rigorously inspecting the wafers at every stage is paramount. Imagine baking a cake and finding a stray hair in the batter, not very appetizing, right? Similarly, any contaminants or defects on a microchip can lead to malfunctions and render the chip useless. To prevent this, chip manufacturing takes place in ultra-clean rooms called fabs, where the air is filtered to remove even the tiniest particles. Additionally, sophisticated imaging techniques such as electron microscopy are used to inspect the wafers for any imperfections. Any defective chips are identified and discarded, ensuring that only the highest quality chips make it to the final product. Section 9. From wafer to chip, the final steps. Congratulations, we've made it to the final stage of our microchip journey. After all the intricate layering, etching, doping, and inspections, our silicon wafer is now covered in hundreds or even thousands of tiny, fully formed microchips. The next step is to separate these individual chips from the wafer, like cutting cookies out of a rolled-out sheet of dough. This process is called dicing, and it involves using a diamond saw to precisely cut the wafer into individual chips. Once the chips are separated, they undergo a series of tests to ensure they meet all the performance and functionality requirements. Only the chips that pass these rigorous tests are packaged and shipped off to become the brains of our smartphones, computers, and countless other electronic devices. The packaging process involves encasing each chip in a protective shell that provides electrical connections to the outside world. And there you have it, the incredible journey of how microchips are made. From a humble grain of sand to a technological marvel, The process is a testament to human ingenuity and our relentless pursuit of innovation. So the next time you unlock your smartphone or browse the internet, take a moment to appreciate the tiny silicon wonders that make it all possible.